Alright class, let's go through this problem carefully and understand the physics step by step. So what we have here is a small block of mass 50 grams that slides down a frictionless surface from a height h equal to 20 centimeters, and at the bottom it collides inelastically with a uniform rod of mass 100 grams and length 40 centimeters. Now the rod pivots about its fixed point O and swings through an angle theta before momentarily stopping. And our goal here, or the question, is to find the angle theta at which the rod stops. So step 1 is to find the speed of the block just before the collision. Now, since the block slides down frictionlessly, we apply energy conservation between its initial and final positions, or mgh is equal to half mv square. Then solving for v, we get v is equal to square root of 2gh, and when you substitute the values, you get v equals 1.98 meters per second. So just before the collision, the block is moving at 1.98 meters per second. Now, step 2 would be to apply angular momentum conservation. Now, since the block sticks to the rod, it's an inelastic collision. That means energy is not conserved. But you see, angular momentum is conserved since no external torque acts on the system at the moment of collision. So, the angular momentum before collision is given by L initial is equal to d cross p, where p is the linear momentum of the box, that is mv. So this equals dmv sine 90, since the angle between p and d is 90 degrees, or simply dmv. And remember, although this mass is moving in a linear fashion just before it hits the rod, yet it has an angular momentum about this point. Then substituting the values, we get L initial is equal to 0.4 times 0.05 times 1.98 meters per second, which equals 0.0396 kilogram meter square per second. Now we find the moment of inertia of the system after the collision. So here the rod's moment of inertia about O is 1 by 3 md square, which when you plug in the values equals 0.00533 kilogram meter square. Now the block stuck at the end of the rod contributes its own moment of inertia, and that equals md square, which equals 0.008 kilogram meter square. So the total moment of inertia is I total equals I rod plus I block, which equals 0.01333 kilogram meter square. Now using angular momentum conservation, we get L initial is equal to L final, or L initial is equal to I total into omega, and solving for omega, we get omega equals L initial upon I total, or 0.0396 upon 0.01333, which equals about 2.97 radians per second. So right after the collision, the rod starts rotating at 2.97 radians per second. Now step 3 is to convert rotational kinetic energy into potential energy. So as the rod swings up, its rotational kinetic energy is converted into gravitational potential energy, and the system will momentarily stop when all of its kinetic energy, that is the rotational kinetic energy, has turned into potential energy. Now the initial rotational kinetic energy is half I total times omega square, which equals half into 0.01333 times 2.97, which we just calculated, and this equals 0.059 joules. Now let's find the change in potential energy. So the block moves up by h is equal to d minus d cos theta, or d times 1 minus cos theta. And therefore, the rod's center of mass moves up by half of that, or h rod is equal to d by 2 times 1 minus cos theta. So the total potential energy gained is PE is equal to mgh plus mgh rod, which when you plug in the values, this expression reduces to 0.392 times 1 minus cos theta. Now, since the rotational kinetic energy initial is equal to potential energy final, we set them equal, or 0.059 equals 0.392 into 1 minus cos theta. That is basically what we're saying is the gain in potential energy of the system has come at the cost of reduction in the rotational kinetic energy. So when you solve for theta over here, what you get is theta is equal to 32 degrees.